Hi, welcome to the bonus lecture of the glacier part of the Geos 119, 120. I kind of put this lecture together, almost improvised it in the sense that it wasn't in the curriculum, but I decided that I could give you a brief overview about like my kind of work and show some cool field pictures and talk a bit more about what it is to be a grad student in glaciology, just as a wrap up of everything we've been doing, and also to give you a glimpse of the fact that glaciology is a huge field, and that it's not because you're a PhD student in that field that you absolutely master all of the aspects of it. So yeah, there won't be any exam question or any work on that part of this lecture. So just take it as, I don't know, as a video, a bonus video if you wanna watch it. So the funny thing about studying glaciology is that it's kind of a weird field in the sense that it's at the crossroad of many different science fields in themselves. It's not like if you are a mathematician or even like a biologist, you have very different specializations. It's the same with glaciology. When you say I study glaciology, if you talk to another glaciologist, you might have to specify what you are already studying, like geochemistry, in the sense that, for example, what is the geochemical composition of ice and stuff like that, sedimentology, geophysics, engineering, ecology, biology, oceanography, climatology, all of these fields can be included in glaciology, which is why it's such a varied and wide field, is because you need all these experts studying this topic in order to make sense of all that you see out there. And in my particular case, and that's what I'm gonna describe a bit during this bonus lecture, is the topic of geophysics. And by geophysics, so I mean studying the movement of ice, studying the physics of ice, studying the exploration of data, how to gather data from geophysical techniques, so radar work, seismology, but also capturing air temperature, solar radiation, and all of that in order to put this data into models and see what's going to happen to our glaciers in the future. I wanted to do a brief overview of how science usually happens. So take all of what I'm saying with a big grain of salt, in the sense that I'm a very early career scientist. I'm a baby scientist right now, and all that I'm saying is probably not very enlightened about how things actually happen. From what I saw and understood, that's usually though how things unfold, where usually when you want to work on something, when you're a researcher or professor, the first phase is that, well, the saying is do the work first and then get paid for it. But ideally, in theory, what happens is that you get an idea that you want to work on, you have an answer, a question that you want to answer, you do some preliminary work to show that you have the capacity to answer that, and you write what we call a proposal, where you're going to describe the work you're going to do, you're going to budget things and convince a committee of people that it's worth giving money to you so you can work on that and finally lead your project. So that's the phase one: get the idea, get the money, you need funding, you need to present that your ideas are worth studying, and then eventually you get money for that. So the second phase would be research and writing. So you get your funds, people trust you with the fact that you can lead your project. So what you're going to do is continue working on those ideas that you had. If they change, that's all right. That's also, part of science, doing things and realizing you were not doing them the right way, or that maybe the question is too difficult to answer. And so you continue to do that, and eventually you build up understanding of your data, of your methods, and you have to what we call publish those results, meaning that you're going to write a report on all these findings, how you took that data, how you measured things, how you interpret these, and they're all going to be peer reviewed by peer researchers. They're going to validate your work and say, okay, this holds. That's not completely imagination or anything like that. That is real, and this person is doing a good job at analyzing data that they have. And so basically that whole phase of publication is just communicating those answers, those findings to the community. Phase 3, I'm not there yet. I actually don't even know why I put phase 3, because we like to divide things into 3 steps usually in science. But what is important is that whenever you communicate, whatever you find, you communicate that to the others. And so whatever findings you have can be transmitted to other people who have other set of skills and strengths, and therefore that's how you build up science, and you kind of push the boundary of knowledge by showing to others what you've discovered, and eventually inspiring them to continue in that direction or try something different. So how is that research organized? And that is kind of particularly adapted to my case, where we have a question that we want to answer. In the case of my PhD, that question is, what's going to happen to the Sitlang Glacier that's in Southeast Alaska? And what happens is that we start with data that we already have, or we prepare how we will collect new data that we anticipate will be useful to answer this question. So we have a lot of satellite images from NASA and ESA, ESA being basically the European NASA. And those images, luckily, are available for free. Sometimes satellite images, you have to pay for them. In that case, you include that in your proposal. It's a budgeting issue. You can have airborne pictures, but you also have fieldwork data. So you're going to go on the field, bring instruments on the field, and gather data that you can't have access to from satellites or planes or helicopters or things like that, drones sometimes. And once you have all the data, you use computers to treat all that, to understand how it works. You do what you call data science, basically. You're going to analyze how all those data sets can interact with each other, what they can explain. And once you have a good understanding of what's happening to your glacier, you create models. And models are going to do 2 things. They're first going to test and verify that you actually understood what you did correctly. And then they are going to be used to simplify your problem and allow you to project results of, for example, in the specific case, the Sitlang Glacier in the future. By model, I mean recreating your objects of study, so a glacier in that case, into a computer, so you can kind of turn the knobs of important parameters like air temperatures or snowfall. For those who are taking Geos 120, we did a lab number 2 that was like a very simplified model, but that was the idea of a model. You have something on a computer, and whenever you modify a parameter, you see what's happening to the glacier. And all of that is based on your understanding on physical laws. And so that's the goal of it, gathering data, putting that into a model, or creating a model in our case, and then see what's going to happen. That's my object of study, the Sitlang Glacier. So I say my, but we are actually 10 people working on that. So it's a pretty big glacier, roughly the size of Rhode Island. Actually, I studied both, like the Sewell Glacier and Sitlang Glacier. It's a giant piece of ice here, located in Southeast Alaska, at the tip of that red, at that red point at the tip of my pointer. Just to give you an idea about how much ice is, lying here in that lobe at the feet of the mountain. This is an Boeing, whatever, I don't remember the number, and the Eiffel Tower. And this is the amount of ice that is in that big lobe, big pancake of ice. And the Eiffel Tower is just here at the tip of the pointer. It's so small that you can barely see it. So it's a lot of ice. And you melt all of that in that area. it might induce some changes. And our job is to measure how much this glacier is melting and what kind of impact its disappearance would have on the landscape. That's the same amount of ice close to Denali. Denali is just here. So again, pretty big amount, pretty big glacier, yeah. So what is my PhD about? Sorry, it's going to talk about me, I guess, during this lecture. It's just, take me as an example of what being a PhD student can be. So 90% of the work I do, of the time I spend, it's on a computer. I look at my computer, I treat the data there. I work a lot with what we call coding, where we are going to use the computers to do tasks that would be way too strenuous, too hard to do as humans. And we try and understand what's happening. And 10%, about 10% of my time is spent on the field collecting new data that we can't get from just satellite images. So who is fit to do a PhD? Well, honestly, it can be, we have all sorts of profiles that do PhD. It's not necessarily the person who was always first at school of their class or something like that. If you take my case, I was actually, I wouldn't say I was bad at school, but I was definitely not good. I was right in the average. And eventually I found a passion and I pursued it. I'm saying that I'm also aware that I'm European and very privileged in the fact that we don't have to pay that much money for college there. So PhD, unfortunately, is still pretty much a very privileged population where you can afford a bachelor and you can afford to be kind of sustained after that, because working as a grad student doesn't pay big bucks. We are paid the minimum wage, and so, you know, in order to sustain that lifestyle, it's definitely easier if you have some financial support. So that's something we have to keep in mind and remind ourselves that we are very privileged in that position. But my core message here was that it's not because you feel that you're bad at maths or bad at physics that you can't do something like a PhD. PhD is basically being overworked for a passion. So yeah, you'll be asked to work a lot, but honestly, in my case, it's worth it. I enjoy it. And every day at work is pretty cool. I wouldn't say I don't feel like working, but you know, I'm happy to get up in the morning and be like, I'm gonna work on some data today. This is kind of what happens on my computer. I do much more stuff, and a lot of it is also just Googling and looking on the internet. That's what we call code. In that case, the language is Python. So basically, we give commands to a computer. We're going to tell it, do that very specific task or that very specific task. And a lot of those tasks are basic, pure math. And from these mathematical operations, then we get results that we can then analyze. So we are basically building up stories as researchers. We see something and we make a story with that. And it's very important to not make a story with your point of view and subjective story. We try to be as objective as possible, even though it's difficult. Try to get the data to tell a story rather than us instillating our own narrative in that. A lot of that work is also about communication, and a few times per year you have to present in front of your colleagues or more general public, like here, what you've been doing during the year, because sometimes you discover interesting things or you develop methods that are worth sharing. Unfortunately, I always kind of look like a mad scientist when I talk, so I guess yeah, it's gonna follow me for a long time, but it's super fun because to do that, because you really got to transmit your passion to people, to show what you've been working on, to defend that, and eventually you get a lot of very constructive criticism that either breaks you apart or no, most of the time that encourages you to be like, okay, I'm gonna modify my method or work with that person that understands way more than me on this particular topic. So communication is a basic skill that every researcher has to face at some point in their career. So now I'm just going to basically show you a couple of videos and pictures from the field and try to say what's the story behind all that. So that was taken on Sourdough Glacier. It's a rock glacier, so covered by a thick, not super thick, but like 2, 3, 4 meters of rocks. And that's in McCarthy. It's in Southeast Alaska. I don't know if I can say southeast of South Central Alaska. And what we were doing there, we were basically working for NASA, where the goal was to test techniques to detect if there was ice below those rocks, and eventually assess if those techniques would be usable for Martian exploration. So we had a drone here with a radar that was flying above the rocks and trying to see if there was ice below. Here I'm hitting with a hammer on some rocks, and we study how that shock propagates through the rocks with like those instruments here, and we can measure how thick the rock layers are. So that was a pretty cool field work, about like 3 weeks on the field. And we tested, what was nice is that we tested a large array of methods. So it wasn't boring at all, in the sense that every day was a bit different from the other. We had to think about, oh, we have this problem, or that instrument broke down. So how can we modify our plan and still manage to answer the big question that we are trying to answer. So super interesting field work, and Southeast Alaska, McCarthy is absolutely stunning. Another thing is, in my case, I started the PhD thinking I would work a lot with climatological data, so air temperature, air precipitation, so how much did it rain, but also how much solar input radiation do we get, how warm does it get on the ice or on the surface of the ice. And those instruments are really finicky, and nature hates them. So those are failed field campaigns where not everything, actually, when you go on the field, things rarely happen according to plan. You have to improvise all the time. And sometimes it's not enough. You just can't gather data properly because you got an avalanche bending your weather station, or a bear thought that would be a pretty good scratching spot and put all of his weight on that and put it on the ground. So yeah, science is finicky, science is hard, and definitely improvise a lot of time. So it's important to be able to mitigate for those risks when they and those hazards, and also accept you have to do a lot of work on accepting fate sometimes when you do science, and be like, okay, well, I guess those measurements were not meant to be, and have a plan B for all of that. That's why we like satellites, because usually satellites are so expensive that they work in the sense that we really have a lot of people working on them, working hard to make sure everything goes according to plan. And satellites have the advantage of taking pictures of the Earth all the time, making them mostly available for free if it's a NASA satellite. And this is kind of what we get. I think those are Landsat images. So Landsat is a pretty cool NASA mission that started in early 1970s. So it's been taking pictures of the Earth for roughly 50 years. And we can analyze those images, kind of come back 50 years in time and see what changes have happened on the cryosphere. So yeah, kudos to those. Another thing, going back to the field, we can kind of validate whatever the satellites see from space and validate that on the ground at more precise at a more precise scale. So for example, here we have a camera that's inside that white box that's taking time-lapse pictures every hour or so of this particular area. So here we thought that lake was growing into the ice, and that was going to be the entry point for the glacier to start melting rapidly. Turns out that that was actually the most boring time-lapse camera we ever put on a glacier, because nothing really happened. So that was interesting to be proven wrong by the glacier on that case. Here is, on the right, is that weather station standing proudly before being destroyed by the avalanche. So that's what it's supposed to look like. And it's kind of working. Oh, here I have just a video showing, I think, a moulin on the Kennicott Glacier in Southeast Alaska, in McCarthy. It was a pretty cool glacier, and I was helping. That was last September, one of the researchers here for his fieldwork, and we were drilling holes into the ice and measuring how much debris cover impacts the melt of the ice. Does it insulate the ice from the sun, or does it enhance the melt? Okay, yeah, next one. This is a time lapse from satellite pictures. As I said, like 50 years of images put together and showing you how the ice moves. And that's mesmerizing. It's completely hypnotic, and shows how powerful it is to have satellites that are taking pictures of the planet all the time. The only thing is that we are relying on weather. We are relying on whenever the satellites are actually passing above, transiting above our area of interest. So in that case, you have images approximately every 16 days, but most of the time, because it's Southeast Alaska, the weather is crappy. So basically we have only a few images, but that's enough to do some science. Here is just a picture of what some of the people I did field work with on the Sourdough Glacier. You can see I'm equipped for rain, and the others are not necessarily. I was happy that day because rain was definitely going to blast us for a few hours later. What I had on my back was a backpack with a radar. So I was holding that on the glacier, kind of like if I had a tail following me behind for, I don't know, 60 feet, and that instrument was sending a radar wave through the rocks and trying to assess how thick the rock cover is and if there is ice below. So that was one of the techniques that we tested. These are just pictures from the Kennicott field in McCarthy. Here on the left, we were drilling holes into the ice to put mass balance stakes or ablation stakes. If you remember lecture 2, that's how we measure how much the glacier is melting. We put those stakes at the beginning of the melt season, and then we come back a few months later to see by how much they're sticking out of the surface. And in order to do that, you have a steam drill. So that's that thing here. We put water inside, then we lock it, and it can be pressured. It's like a big pressure cooker. We have some kind of stove down there, and what you do is that you boil that water, and because it's sealed, the pressure is going to increase, and all that vapor is going into that hose and exiting there. And you have like some vapor that exits the hose at some pressure, and you can drill very efficiently through the ice. I mean, very efficiently. It's not super fast either, but it takes, when it's working, it takes about 10 minutes to drill like 30 feet of ice, of a hole 30 feet deep. In our case, that thing never really worked, and it took us 1 hour per hole, and it was really cold. So interesting field work. And here we're just collecting samples of till in front of the glacier to see like what kind of bedrock is below the glacier and stuff like that. And I think that's my last slide. Yeah, it's just nice. No, it's not my last slide, but that's just a nice picture showing what it looks like on the Sitlan Glacier. It's a gigantic pancake of ice. You have Mount St. Elias there. We have the helicopter that's just hauling us on the glacier, because we just can't walk everywhere. It's just way too big, and there are too many crevasses. So here we were setting up a tripod that has a GPS antenna. The nice thing with GPS antennas is that they record very often, like every 5 minutes, the position of where they are. So you can track how the ice is moving, but also how it is melting, because those antennas also record how high above seawater they are, how high above sea level they are. There's like a solar panel to sustain all of these instruments in energy. And yeah, the helicopter that was just moving us everywhere. And I think that's like the last video that I wanted to show is just a nice time lapse of the the Malaspina, the Sitline Glacier. Yeah, I'm very, very lucky to be a PhD student here, and I'm aware of that. I just wanted to say that it was fun to teach that course again. I'm reading all of your assignments. I'm really reading through the feedback and seeing what worked, what we didn't work. So my take-home message is that I hope you enjoyed that course. I hope it seems like everybody learned a lot of stuff, so I'm super happy with that. We actually dived pretty deep into some of these topics. So you have a very comprehensive overview of glaciers right now, of the cryosphere. So don't hesitate to come back to those videos or ask me for material if you want it, or if you want, I don't know, present it to friends or talk about glaciers. Or what I hope is that whenever you're gonna be in the mountains at some point, and if you see a glacier, be like, I know about that stuff and I can explain some of these processes. So yeah, thank you for following that course. I hope you have had fun throughout the 3 sections. It's definitely a super nice course, even though it's only online. We always prefer when it's in person, so we can interact better, and the labs are also better in that regard. But it's great nonetheless that it's online, because we can broadcast that course to so many more people. It's great to see students, non-students, traditional, non-traditional students, all of these variety of people taking the class with their families or not, in Alaska or outside Alaska. So it was absolutely amazing to see how far we just can reach with just a video. So yeah, don't hesitate to stop me if you see me on campus. I'll be happy to talk to you and hear about what you're doing, how you're doing, and what you thought of the course. So have a nice one. Have a great end of the semester. Good luck, you're almost there. And don't forget about that bonus quiz next week that will be used to eventually increase the worst grade that you have in the glacier quiz section. So that quiz will be on Tuesday. The final exam will be on Wednesday. And yeah, in the meantime, I hope you have fun, and I'll see you later. Bye.